Here the statement of the problem is, in a hydrogen atom, the electron makes 6.6 into 10 raised to power 15 revolutions per second around the nucleus in an orbit of radius 0.5 into 10 raised to power minus 10 meter. That means you have been given the radius of the orbit in which the electron is revolving around the nucleus, and you have been given the frequency of revolution as well. That how many turns it takes in 1 second, right? That is what you mean by frequency. It is equivalent to a current nearly, and then there are 4 options. So this you might have read in your general theory sessions, that whenever a charge q oscillates into a circular path, or like revolves into a circular path, it actually carries an equivalent current. Why so? Let's talk about it. So when a charge q is flowing through the, or like is passing through the circular path again and again, now let's take a point A over there. Let's take a point A over the circular path. Now let's suppose it is having a time period of t seconds, capital T seconds. That means it takes capital T seconds to revolve into a complete circle, right? Okay, so now it starts from point A, let's say at certain moment, let's say at t naught is t is equal to 0. Then the next time it will cross through point A will be at t is equal to t. Then the next time it will cross at A, it will be at t is equal to 2t. So can you tell me what is the amount of charge passing through A per unit time? That's the average current, right? Amount of charge passing through any point per unit time. That's the average current, right? So from A, what I write? From A, Q charge flows after every t seconds. Do you agree with that? Yes. So in t seconds, the amount of charge flowing from a particular point is Q coulomb. So in 1 second, the amount of average charge flowing through a particular point will be Q by T, right? So that's why the equivalent current in the circular path at any point will be Q by T. That's the I average. That's the equivalent current due to the flow of charge. So that's why we write this formula, I is equal to Q by T. Now, in the formulation in the question, you might be given the time period directly. You might be given the frequency, which is 1 upon time period. You might be given omega as well, the angular frequency of the charge, which is equal to 2 pi by capital T. Whatever relation you have been given, or whatever variables you have been given, whatever quantities you have been given, you should use this formula in terms of those quantities. Here you have been given the frequency. So 1 by T I'll replace with F. So that's why my I comes out to be Q into F. Now Q is the magnitude of the charge. What is the magnitude of the charge of the electron? That's 1.6 into 10 raised to power minus 19, correct? That is 1.6 into 10 raised to power minus 19 multiplied by, what is the frequency given? 6.6 into 10 raised to power 15, correct? 6.6 into 10 raised to power 15. This, if you solve, comes out to be 1.6 into 6.6 into 10 raised to power minus 19 plus 15 is minus 4. This almost comes out to be 1. This 1.6. So this is almost equal to 0.1. 1.6 into, sorry, this is almost equal to 10. 1.6 into 6.6. That's almost equal to 10, right? So we can write this nearly equal to 10 into 10 raised to power minus 10 into 10 raised to power minus 4, which is nearly equal to 1 milliampere. That's why here the current is nearly equal to 1 milliampere. Let's look into the answer. Yeah, 10.56 into 10 raised to power minus 4. That is nearly equal to 1 milliampere, correct? Now let's look into the options. Option B in this case will be the correct option. See, these problems which are given in the beginning in the sheet, in the DPP, they are the problems which involves the basic fundamental formulas. So there are some quantities defined in the beginning. Say for example, the velocity. Say for example, the mobility of electron or mobility of a charge, right, in a conductor. So there are some definitions, some fundamental definitions which are given, and you should remember the definitions and the formula associated with it. So that's why the initial problems are formula based, but these are crucial formulas. You should remember them. So the statement says a potential difference of 6 volt is applied across a conductor of length 0.12 meter. The drift velocity of an electron is, and then the mobility of electron is given to be 5.6 into 10 raised to power minus 6 meter square per voltage second, per volt second, right? Okay. So the two terms they are using, mobility of electron and drift velocity. Basically, there's a formula. There is a relation in between two. So mobility of a charge is defined as drift velocity per unit electric field. So when you apply the electric field, the electrons start drifting from one end of the conductor to other end of the conductor, right? Right? From negative end or from the lower potential to the higher potential, to the positive end. Electron starts drifting like this, opposite to the electric field. So if let's say this is the material, this is positive terminal of the battery, this is negative terminal of the battery, then the electric field actually gets generated like this. So electrons start drifting like this, opposite to electric field, right? With some drift velocity which we know as Vd. Then what is the mobility defined as? The mobility of the electron here is defined as drift velocity per unit electric field, right? So if you know this relation, that mu, that mobility is equal to drift velocity per unit electric field, yani Vd by E, right? If you know the relation mu is equal to Vd by E, then of course the system is simple to you, right? Okay, let's look into the discussion. Okay, now this is the figure given to you, right? Okay, now we know the formula mu is equal to Vd by E. So, okay, drift velocity is equal to mu times E. Now basically you know mu, you know potential difference across the conductor, you know length of the conductor, you don't know the electric field. So what is the formula for electric field in terms of potential difference? So say for example, this is the positive terminal, this is a negative terminal of the conductor, and the distance between them, between the positive and the negative terminal, is 0.12 meter. So the potential difference delta V will be equal to, what is the potential difference created by the battery? 6 volt, right? So the electric field inside the conductor, E, is given as delta V by length of the conductor, L. That is given as 6 upon 0.12 volt per meter. Correct? So if I just put the value, Vd is equal to mu times E. Mu is 5.6 into 10 raised to power minus 6 multiplied by electric field. That is 6 upon 0.12. If you just solve this, right? If you just solve this, okay, just remove this, put a 0, and 6 1 ja 6, 6 2 ja 12. Right? So this comes out to be 218 to 10 raised to power minus 6. Right? That's Vd, meters per second, right? The SI unit for Vd, drift velocity, is meters per second, correct? So the answer here is 2.8 into 10 raised to power minus 4 meters per second. That's the answer in this case. See this? So let's look into the options now. Option D in this case will be the correct option. Again, a fundamental problem. The statement is determine the current flowing in ampere through an element at time t is equal to 2 seconds if the charge flow is given as q is equal to 2t square plus 3 coulombs, right? So charge as a function of time is given to you. What you know is charge flowing as a function of time. So at t is equal to 0, so charge was 3 coulomb, right? Q flowing was 3 coulomb, right? And then at t is equal to 1, if you calculate q, the amount of charge which is flowing, it's t is equal to 1, if you put, that will be 5 coulomb, right? So as the time is increasing, the charge is flowing with an increasing rate, right? Okay. Now, how the current is defined? The current is defined as dq by dt, correct? Correct. Now, if q is a function of time, the charge flowing through an element is a function of time, that is 2t square by 3, 2t square plus 3, then I will be given as differentiation of this. Correct? Now, if you differentiate that, you will get this as 4t. Is current also a function of time in this case? Yes. It might be a constant as well. Had dq by dt been a constant, then I might have been a constant. But here, I is a function of time as well, right? Now, you are supposed to get the current to the element at t is equal to 2 seconds. We say that as instantaneous current. When something is a function of time and we put a certain time to get the value of that particular thing, then at that moment the value of this thing is called instantaneous value. So when we put t is equal to 2 seconds, we get instantaneous current at t is equal to 2 seconds, and that comes out to be 8 ampere in this case. Correct? Correct. You might be asked the average value of current as well. The average value of current, they might ask you, what is the average current? What is the average current flown from 0 to 2 seconds? There are multiple options to do this. How? You can do this as delta Q by delta T. I'm just giving you an example that what else can be asked in this, right? In this case, your answer is 8 ampere, that's okay. But suppose you have been asked, what is the average current in between 0 to 2 seconds? So the average current means the total charge flown divided by the total time taken. So the total charge flown is Q at 2 seconds minus Q at 0 seconds divided by delta T is 2 minus 0. Now Q at 2, if you put the value, Q at 2, it comes out to be 2 to the 4 to the 8 plus 3, 11. 11 minus Q at 0. What is the charge at 0, right? So at 0, if you put, your charge comes out to be 3, correct? Okay. Then here, the value of average current for 0 to 2 seconds comes out to be 11 minus 3, that is equal to 8 divided by 2, that's equal to 4 ampere. So suppose somebody asks you, what is the average current flown in 2 seconds, 0 to 2 seconds? Your answer should be 4 ampere. Somebody asks you, what is the instantaneous current at t is equal to 2 seconds? Your answer should be 8 ampere, right? In this case, the instantaneous current has been asked. So it's 8 ampere. Let's look into the options now. Option D in this case will be the correct option. Here the statement is, a straight conductor of uniform cross section carrier, it carries a current I. Let S be the specific charge of an electron. The momentum of all the free electron per unit length of the conductor due to their drift velocities only is. Please understand this. So basically here you should be aware of the terminologies they have used. So they have used a symbol S. S be the specific charge of an electron. That means here S, by saying S, they mean charge of electron divided by mass of electron. Mass of a single electron. Charge of a single electron divided by mass of the single electron. That is what they mean by S, right? And you are supposed to calculate the momentum of all the free electrons per unit length of the conductor due to their drift velocities only. Good question. Please look into it. Okay. Let's say this is the system given to you. A potential difference is being created by the battery on the two terminals of the conductor, and the current is flowing. Through the conductor. Now, when the potential difference is applied, basically you apply an electric field. So if you apply an electric field, the electrons there inside the conductor, they start drifting with a drift velocity Vd, right? Right? From negative terminal to the positive terminal inside the conductor. Correct. Now, you know that the current is given as I is equal to NEA times Vd. You have read that. You have read this equation in the theory, right? How it comes from. You know that, right? Where N is the number of electron per unit volume, right? Number of electron per unit volume. E is the charge of the electron, charge of one electron. A is the cross-sectional area. Vd is the drift velocity and I is the current. You know that, right? And you are supposed to calculate the momentum of all the electron due to drift velocity only per unit length. So let's suppose you take a unit length, L is equal to 1 meter. Then the cross section area will be A only, right? So how many electrons are there in that section? What is the volume? What is the volume of what is the volume of section of conductor of unit length? So if it is having a unit length, then the volume will be equal to 1, that is the length multiplied by cross-sectional area. That is the volume. Now, what is the number of electron in this volume? The number of electron over there, the number of electron in it will be equal to number density, that is the number of electrons per unit volume, multiplied by the volume, which is A meter cube. 1 into A, that's A, right? So this is the number of electron into the segment where you want to calculate the momentum, right? Okay. Now each electron is having a velocity, drift velocity Vd, against the electric field. That means in the same direction, against the electric field. So say for example, electric field is like this. So each electron will have Vd like this. So in that section, what is the total momentum? What is the total momentum? Let's say I talk about the magnitude. What is the total momentum? That is equal to number of electrons multiplied by their mass multiplied by drift velocity. So basically this is the momentum. This is the formula for momentum. Momentum P of all the electrons which are there into the segment. How many electrons are there into the segment? Na electrons. And each electron is having a mass m and it is moving with a velocity v. So all the electrons in that segment will have a momentum Na into mvd, right? This I could do because vd for each electron was in the same direction. So I just directly added that, correct? Now this is the momentum, this is the current. What do? You divide I by P. You divide I, the equation of I, by the equation of P. So what you get is I by P is equal to NEAVD divided by, what is P? That's NAMVD. VD cancels, AA cancels, N also cancels. So I by P comes out to be E by M. Now what is E by M? I already told you, right? E by M is S. So what is momentum P? That's I by S, correct? So in this case, the momentum comes out to be I by S, correct? Now let's look into the options. Option B in this case will be the correct option. Here the statement is 2 wires each of radius of cross section R, right? The radius of cross section is given to be R for both the wires, for both the sections of the wire. But of different materials are to be connected together. Different materials means the electron density will be different in both the materials. End to end in series. So the wires are connected in series. Take them as two resistances, right? Two resistive wires. Now, if the densities of the charge carriers in the two wires are in the ratio 1:4, then the drift velocity of electrons in the two wires will be in the ratio. There are 4 options given to you. So basically you have to figure out what is the ratio of the drift velocities in the two wires which are being connected in series through a battery, and they are having equal radius of cross section. That means equal cross sectional area, correct? Radius of cross section equal means the cross sectional area equal. Okay, now let's talk about this. So basically when you connect the wire in series and you connect the ends, the two ends from the battery, positive and negative terminal, a current flows into the circuit. Let's say the current flows is I. Now because they are in series, you might have studied that in theory, or you will study that in theory, that whenever the resistances or the wires are connected in series, the current is same. That means the same current is flowing through both the wires, right? Now in any wire, the current flown is given by the formula I is equal to NE times area of cross section times drift velocity, NEAVD, correct? So for the first wire, if I write, the current I will be N. N is the charge density, electron density, number of electrons per unit volume. That is, let's say N1. How much? N1 into electronic charge is E only, correct? Multiplied by cross-sectional area. That will be pi r square because r is the radius of cross-section, correct? Multiplied by drift velocity of the electron in the first wire, correct? Now, for the second wire, the same current I. Why same current I? Because both the sections are in series. So the same current I is given as the charge density in the second wire multiplied by E multiplied by area of cross section multiplied by VD2, right? Now, if you look into these two equations, this will simply tell you that if you put, so basically the left hand sides are equal, so the right hand sides must also be equal. So if you put this equal to this, what you get? Basically you get N1 times VD1 is equal to N2 times VD2, correct? Now you have already been given the ratio of N1 and N2, correct? The N1 and N2, the ratio is given as 1:4, correct? N1 by N2 is equal to VD2 by VD1. And N1 by N2 have already been given as 1:4. So VD1 is to VD2. The ratio of the drift velocities in the first and in the second will be given as 4:1, correct? So the answer in this case will be 4:1. Let's look into the options. Option C in this case will be the correct option.